All right, this is Chapter 8 test review. Um, Without further ado, let's get going. Before you get too far into this, make sure you have your green packets out, especially mainly for this page, the T distribution page, known as Table B. This is where we get our T stars, and also have your formula sheet or your cheat sheet out, this one here. A main idea for the entire chapter is distinguishing this column from this column. Proportions from means. All right, let's go. First one, in the city of Statstown, 20%. So right there, you know it's a proportion question. Of all the residents, they're Hispanic. Of all of the residents, 50 will be randomly selected to win a free dinner with me. Oh, yes. To dive deeper into all their statistics questions. Oh, man, that's like the prize of a lifetime. What are the mean and standard deviation of the sampling distribution of the proportion of Hispanic residents for samples of this size? So the mean, first of all, is a proportion. So right away I see these two. These are not proportions. They are quantities. So those are bad. So it's C, D, or E. Then the other, maybe just bigger picture here, like um, they're all the same, right? But the average p hat, the average sample proportion will equal the population proportion of 0.20. Then this is what will separate these three. This is the standard error formula, also known as the standard deviation formula. And the main thing is which one is correct. It's this one because it's 0.20 and 0.80. This one is tricking you if you thought that 20% was 0.02. And this one doesn't even have decimals, so it's C. Number two, according to a survey, 15.2% of housing units in Rosemount are rentals. So we're doing a percent one again. A sample of 200 housing units will be randomly selected. Which of the following must be true for the sampling distribution of the sample proportion of housing units in the large city that are rentals to be approximately normal? In other words, what has to be true for this to be approximately normal? Um, this question is tricky because the wrong answers sound appealing. They sound like things we talk about. We talk about this. Does the distribution have to be, must it be normal for any sample from it to be normal? That is not required, but it would be helpful. This is also something we talk about more often with sample means, not percents. So it is not A. B, the sample size must be greater than 30. This is the CLT, and that is also not for proportions, that is for means. So you're crossing off those two. Letter C, this formula that they have here, this is the formula from up here that we just did right here. And it says this is the standard error formula. Does the standard error or the standard deviation have to be at least 10? No. Um, they're crossing their wires here. If you looked at your cheat sheet, large counts have to be at least 10, not this, okay? You have to have 10 successes and 10 failures. So they're kind of mixing two things there and trying to trick you. So it's not that one. It is going to be D because this is how you find your successes. 200 houses times the probability of a rental. This would tell you how many houses are rentals. And then this would be how many houses are not rentals. In this case, we call those successes and failures. They have to be at least 10. So that's our winner. D is also something you have heard, but it's just misleading. Does the sample size have to be less than 10% of the population? That is a good thing, but that is not what makes it normal. That is what makes it independent. And that is not what the question is asking. Number three, a sample of batteries will be selected from a large population in which 2% of the items are defective. Of the following, which is the least value, the smallest value for a sample size that will allow the sampling distribution to be assumed approximately normal. So that's kind of piggybacking off of this one, right? We had to have 10 successes and failures. So take the 2%, that is your P, and we know that n times 0.02 has to be at least 10. And we also know that n times 1 minus 0.02 has to be at least 10. If you check these on the calculator, you know, you would go 10 divided by 0.02, and that's the 500, and 10 divided by 1 minus 0.02 would be the other one, those two numbers that I got there. Now, I'm going to go with the larger one, right? Because I have to be able to get 10 of each of these. If I picked a sample size of 10, and maybe you're thinking, there it is, there's my 10. Well, if I put a 10 into right here, that is not going to get me 10 successes, right? 10 times 0.02 is 0.2. So that's not going to work. So it's got to be the 500. Okay. Um, Number 4, the distribution of the commute times for Rosemount students has a mean, okay, sample mean. That's our first question of means. So your X bar is 10.8 minutes. That's how long on average it takes students to get to school with a standard deviation of 3.8 minutes. There was a random sample of N employees selected and their commutes were recorded. Okay. What's true about the sampling distribution as the sample size increases from 10 to 20? Um, the first two are not, the mean does not change. If you have a sampling distribution, right, it is always centered at the same place. If you take a larger sample, it doesn't move up, it doesn't move down. Taking a larger sample makes the curve tighter, right? So it makes the standard deviation go down. It does nothing to the mean, okay? So that brings us to does not change, these three. And then it's looking at variance. And you might be like, variance? We don't talk about variance. Variance is, remember this, variance equals standard error squared, or standard deviation squared. So I can find the standard error using this formula. This is on your cheat sheet because we're doing the X bar side, the sample means side. I know S of X is 3.8, right? And then I know the sample size is going to go from 10 to 20, and then I compare these. So what are, this, let me, might be a little misleading. Variance is the standard error squared. So let me just compare them. Does it not change? Does it decrease? Does it increase? Okay, so I'm looking at this. So we've got 3.8 divided by the square root of 10. That's the standard error of a sample size of 10. If you square that, that would be the variance. If you do it with a sample size of 20, let's see, 20. Well, you can compare the very top answer of 1.2 to this one of 0.89. It went down, okay? And that's pretty much all you need. And if you square it, that's technically the variance. So then you compare, that's the variance for sample size 10. That's the variance for sample size 20. So it went down, okay? So it's D. 5. Survey was conducted to determine what percent of college, percent, so we're doing P's and P hats, what percent of college seniors would have chosen to attend a different college if they had known what they know now. In a random sample of 100 seniors, 15 indicated they would have attended a different college. A 97% confidence interval for the percentage of all seniors who would have attended a different college is beep. So this is really just multiple choice. Don't show your work. Just use the calculator to create this interval. Make sure you know it's a percent, so it's a proportion interval. P hat is given to us right here, so it's 15%. is going to be our point estimate. That's going to be the middle of the interval. And then our sample size is 100. So on the calculator, I'm going to go stat tests. This is the capital A, one prop, Z int, and put your numbers in. 15 out of 100 with a 97. It's 97% confidence. And there's your interval, so it's B. The one thing that might catch you is if you're just not careful with the 97. Like if you put 95 on accident like this, you can see that leads you to this one, and it would be pretty easy to just overlook that. Number 6, the FDA wants to estimate the mean, okay, sample mean. So it's the next bar question. The mean mass of bags of red potatoes sold at the grocery stores. The mean mass of the 25 random bags is 5.2 pounds, and the standard deviation was 0.2 pounds. That's your sample standard deviation. All the conditions are met. Which of the following is a 90% confidence interval? Okay, so for the population average. So this is different than this because you don't actually just use the button and get the interval like we did up here. It's all written out like it is on the formula. So you have to put the pieces together. Your X bar is 5.2, so that they all have 5.2. That doesn't help us a lick, okay? T star is going to eliminate some of these. Remember, T star comes from degrees of freedom when you have a sample mean. Just to remind you on the cheat sheet, you have Z stars over here whenever you have a proportion, and you have a T star whenever you have sample means. All right, degrees of freedom is n minus 1. So in this case, the sample size was 25. So my degrees of freedom is 24. I need this and I need this. And I look in my packet now to where they intersect. Uh, yep, this one. Degrees of freedom's down the side, right? So 24 and 90. So that's right here. 1.711. So that limits it to 2 of the answers, to these 2. Just a quick little side note, these are clever distractions because these come up a lot. 1.96 is the z-score for 95%. And you might just think, I think I've seen that before, that could be it. But don't be distracted by these. And then even more so, 90%, you say, ooh, 90%. The 1.645 is the z-star for 90%. Quick reminder, where do you find z-stars? Same table, table B, but way down at the bottom, your z-stars are the infinity row. So there's the 90% one, and there's the 95% one. Here's the 99 one. Those are the most common 3. So it's not those 3. So you're down to these 2, and we should be trying to do the standard deviation divided by the square root of n. So this one is wrong because it doesn't have the square root. It doesn't square root 25, but this one does. Oh, T star is 1.711. All right, number 7. 95% confidence interval for the mean time in hours students spend on homework every week is 4.1 to 10.5 hours. 4.1 to 10. Which of the following is the best interpretation? This pretty much just means, what is your conclusion? At this point, you've written a whole bunch of these, and if you take time to read all of these, none of them are the correct interpretation. It's this one, which you've written over and over and over again, so it should look right. This should be a pretty straightforward question. Yeah, um, it's not it's trying to looking at some of these wrong answers. The probability is 95% that one randomly selected kid is between here and here. That's far too specific. This is more general, right? And we're 95% confident that our interval that we created will capture the mean that we're estimating. All right, 8. A very large high school wants to estimate the proportion of teens that use Snapchat. Oh yeah, good old Snapchat. From previous studies, they expect the proportion p hat to be 0.60, and the staff plans to collect a random sample of teens in the school. They would like to create a 95% confidence interval. Which of the following is the minimum sample size needed to get a margin of error no larger than 0.04? So from your cheat sheet, here's your margin of error formula right here. Let me just point it out to you. It's right here, margin of error, because we're doing a proportion. And what have they given us? They have told us the z-star, sort of, 95%. And I just looked that up a few minutes ago in the video, right? It's on the bottom, on the infinity row right here at 95%. So we have this. Your margin of error is given to you right here, 0.04. And then it says 60% is your p hat, so that's 60, and this is 1 minus 0.60. Now we have to go through the nitty-gritty of solving this. So get your calculators ready. And do not round at all until you've got your final answer, okay? So step 1, you're gonna divide by 1.96. Okay, 0.04, whoops. And I'll write it down, but I'm not gonna round it. I'm gonna leave it on my calculator. Then I've got the square root of 0.60, 0.40 over n. At this point, you square both sides. So just square my answer on the calculator. Boop. Got it. Ugly number. You're going to get scientific notation almost every time right there. Now the square root and the square are inverses, so they cancel. So I've got this. At this point, this decimal and n, we switch their spots, right? I'm multiplying the n over there, and then I'm dividing the scientific notation back. So on my calculator, I guess it would be n equals 0.60 times 0.40 over that scientific notation number. Divided by, and then go grab it like that. So 576.24. Now you always round this up to the next integer higher, because this one is misleading. Okay, it's got to go up, because if you go down, you are actually ever so slightly decreasing your margin of error, and you don't want to do that because it says no more than 0.04. Wait, let me make sure I said that right. If you go down to 576, it would increase your standard deviation. My memory is faulty right now. I can't remember what I said. So you can't go down because it would make the margin of error too big. So you have to go up. All right. Also, if that was like, ugh, you can fall back on this, which we talked about. And you can just do it all in one big line. So like 0.6 times 0.4 divided by margin of error was 0.04 divided by my z-star squared, and it's all in one line. You get the same answer. Number 9. A random sample of 50 kids, okay, was making a 95% confidence interval for the proportion of RHS kids that take AP Stats. Oh yeah, love these kids. It should be way higher than this. Whatever. It's from 0.18 to 0.32. Which of the following statements is correct? We have 4 statements, and then you have to try to, determine which one of these is going to be the one. The first 2 you can pretty much get if you just kind of draw out the interval. It goes from 18 to 32. So the point estimate is the middle. The middle is 0.25, and it sure is. You can add up 0.18 plus 0.32 and divide by 2. So that one's true. Green check mark. Number 2, is the margin of error 7%? Well, there's my picture again. Some of you see that and you're like, yep, up 7 and down 7%. Or you can do 32 minus 18 divided by 2. I should be careful. It's 0.32, right? It's 0.32 minus 0.18. That's 0.32 minus 0.18. Man fag. That's 0.14 divided by 2. That's my margin of error. So we're good here again. Those first two are right. So I can cross off A, and it can't be E because none. Okay, so I'm down to those 3 options. Number 3, a 99% confidence interval would have a larger margin of error. Okay, margin of error, just right? We just did one like that. This is your margin of error formula. If your confidence goes from 95 to 99, what does your z-star do? It goes from 1.96 to 2.576. And if your z-star gets bigger, your whole margin of error is going to get bigger. So yes, this is true. And you can find both of these on the bottom of the packet, right here, one more time, right here and right here. Booyah. So look at that, 1, 2, and 3, they're all true. We're on a roll. Green, make that one green. So it can't be B, okay? So it's C or D. Number 4, doubling the sample size will cut the margin of error in half. This one is so close, but it's just not quite true. When you increase sample size, the margin of error will indeed lessen, but it will not be cut exactly in half by doubling. And the reason is because again, in my standard error formula, you've got your sample size here. It's being square rooted. If it wasn't being square rooted, then this would be a true statement, but it is. So let me show you this in action. The standard error over here, sorry, over here is the original one. So when the sample size was 50 people. So there you have that. That's 0.06. Okay, about a 6% standard deviation. Okay, and then if I do this one, now I have 100, and now I've got 0.043. Did it, so I doubled the 50 to 100. Did this number get cut in half? It did. At this point, I am not changing Z star. I'm only changing this because the only thing changing is N. So 0.06 is not being cut in half because if it was, it would be 0.03 over here. Or if you double this, look, you're not getting 0.06. So this one is sneaky. It is getting smaller, but not exactly by half. So 4 is not true, so it is not D, so the answer is C. All right, we are on to the FRQs. Number 10 is about 3 players on a basketball team have 3 different free throw percentages. Over the course of the season, Nora makes 65, Jenny 75, Ava 80. One day, a guest coach shows up and watches practice and watched one of these players shoot a random sample of 50 free throws, and she made 32 of them. We're going to do a 95% confidence interval. We're going to do the whole shebang. So you have to first name it. This is on your cheat sheet. One sample proportion, Z interval right down here for P. Okay, and here's the other name over there. All right, name it first. Name your parameter, which is what we're measuring. Okay, It is the true proportion of made free throws. And technically, it's for this one player, right? We don't know which player because it doesn't name the player. The conditions, was it random? Well, I think it stated that. Random sample, so I said stated. And let's go here. Yep, check. Large counts, because why am I doing large counts? Just quick reminder, because I'm doing these three conditions right here. Large counts. Did this person have 10 successful shots and 10 unsuccessful shots? She did. She made 32, and then 18 is just 50 minus 32. It's 18. These are both bigger than 10. So we know the distribution. Make sure you state this. The distribution is approximately normal. Okay? It's not sufficient to just say this and this right here. Okay? You have to say why we're even checking this in the first place. And then the last one here, every free throw is what? Blank independent, right? One free throw does not affect the next free throw, especially in practice. So there we go. That's our state and our plan. The do is when you do the work, okay? N is 50. P hat is 32 out of 50. So that's 0.64. And then here's the formula. Again, this is on your cheat sheet on the left side. Now we just need to fill it out. P hat, 0.64 plus or minus Z star. 95% gives us 1.96. Square root of 0.64, 1 minus 0.64 over 50. And then it's just a matter of cranking this out on the calculator. I'm going to start with the square root. Square root of 0.64 times 1 minus 0.64 divided by 50. So that's my standard error, or standard deviation. Multiply that by 1.96 standard deviations, and I'm essentially getting a 0.64 plus or minus about 13%. 64 is the center of the interval. I'm going to add 0.13. Actually, I might as well just add that whole thing. Bloop. That is going to be the high side of the interval. And then I'm going to subtract it to get the low side, the bottom of the interval. So I'm getting 0.506 to 0.773. If I were you at this point, I would definitely check it using the test like this. And it's really, really quick and easy to do. So there you go. Bada bing, bada boom. That's exactly what I got. Make sure you also interpret or write your conclusion or interpret it like I already have. We're 95%. I should put the word confident in there, huh? We're 95% what? Just rearranging here. There we go. Confident that this player's true proportion of made free throws is between those two numbers. Always, there's a follow-up. Does this interval allow this guest coach to clearly identify or determine which player this is? Is it Nora, Jenny, or Ava? Well, Ava's percent does not fall inside this range, so it cannot be Ava. However, Jenny is a 65% shooter. That's within here, and so is, Nora's and Jenny's are both within here. So I can't tell if it's Nora or Jenny, but I can eliminate Ava, but I cannot distinguish between the other two girls. We're kind of assuming here the coach doesn't know the girls. Last question. This is your sample means interval. Researchers want to determine the mean daily screen time for teens, including phones, iPads, laptops, and TVs, A random sample of 84 teens in Minnesota found an average of 7.5 hours a day. That's your X bar, with a standard deviation of 1.8 hours. That's your S sub X. Let's make a 98% confidence interval. So name the procedure. One sample T interval. What is the parameter? It is the mean daily screen time for teens. It's mu. Conditions, once again, random was stated right here. You can maybe put a nice little check mark. Is it going to be normal, approximately normal? This one is not large counts. This is the CLT, and 84 is above 30. So I'm good. Okay, 84 was the sample size up here. Okay, that is N. And then number 3 is the independence. You could say one teenager screen time is independent of all other teenagers, of another teenager. This is a perhaps like a nationwide survey, so I could maybe argue that if two kids are friends, their screen times are kind of linked, but it's pretty safe to say this. Also, if you don't like that argument, you could also do the 10% rule. 84 teenagers is far less than 10% of all teenagers. All right, degrees of freedom, gotta have that. That's gonna be your 84 sample size minus 1, which is 83. And I'm gonna use that to get my T-star. 83 is my degrees of freedom. I also need my 98, and I see where those two things cross. Um, all right. The problem is 83 is not on there. So do I go down to 100 or up to 80? And you always go up the table. The reason being is that when you go up the table, you are getting a slightly bigger T-star, which is more conservative. A larger T-star will make a wider interval, which is more conservative. So we're going to use 80, which will give us this one right here because it was 98%, right? 2.374. All right, so let's piece the interval together. My X bar is 7.5 plus or minus that T star I just looked up times this S sub X, which is 1.8 hours divided by the square root of 84. And let's do a little bit more, and then I'm going to have the calculator give me the interval as well, just to double check my work. 1.8 divided by the square root of 84 whoop, is 0.196. If you multiply that by your T-star, that's the number of standard deviations that we need to include to capture 98% of all the possible samples. So I've got 7.5 plus or minus 0.466. Right? 7.5 is the point estimate. 0.466 is the margin of error. So 7.5 minus, bloop, that's the low end of my interval, 7.03. And then if I add it, oops, if I add it, oops, oh dear, 7.03, let's do 0.466 for now. And I'm going to get, oh, not, sorry, 7.5, that's the point estimate, plus 0.466, 7.966, all right. Now just verify it using the stat menu, tests, number 8, T interval. And oh look, I already have it in there from before, except I need to change this to 84 sample size and a 98% interval. There, my lower and upper are matching. All right, then make your conclusion. We're 98% confident the mean daily screen time for teens is between those two numbers in Hours is the units. Don't forget that. Lastly, a research firm is claiming that the mean daily screen time for teens is actually 8.4 hours. Does our interval support that claim? The answer is no. 8.4 is not inside here. It is above. It would be up here, higher than all of our possible estimates. It's not captured by the interval, therefore the data does not support the claim. It's kind of, we would say that this research firm is overstating the truth. All right, folks, that's all I got for you. Enjoy your studying.